Hi, in this session we shall discuss spin precession. In the previous classes we have developed the basic formalism to describe time evolution in quantum mechanics. Let's now consider an extremely simple example which illustrates some of these ideas. The system we shall consider is an electron in an external magnetic field. We know that electrons are tiny magnets, that is, electrons have a magnetic moment and this magnetic moment interacts with the external magnetic field. So, in order to start to describe the time evolution, we need the Hamiltonian of a spin half system that is subjected to an external magnetic field B vector. So, the next question is how do we get the Hamiltonian? Okay, we know that Hamiltonian is the energy operator. So, let's look at the classical interaction energy. Classically, the interaction energy between mu vector and B vector is simply given by minus mu vector dot B vector. We have already seen this in the first chapter when we discussed the Stern-Gerlach experiment. When we discussed the Stern-Gerlach experiment, we also saw that the magnetic moment is related to the spin. All right, and in SI units, the relation is given by mu vector is equal to GE divided by 2ME S vector, where G, the G factor, it's equal to 2 for electrons. We have already seen this. Now this is in SI units. If we are using CGS units, there would be a C in the denominator here. I think the textbook uses CGS units, but we'll stick with SI units because in the first chapter we used SI units. Now classically the interaction energy is minus mu vector dot B vector, and quantum mechanically this mu vector for a spin half electron is given by E divided by ME S vector. Just put G equal to 2 in the previous expression, so 2 in the numerator and 2 in the denominator will get cancelled, and you get mu vector is equal to E divided by ME S vector. You put it back in here and you get minus E divided by ME S vector dot B vector. Alright, this expression we can take as the quantum mechanical Hamiltonian. This is a method that we usually use. We take the classical mechanical expression and assume that the quantum mechanical expressions have the same form. Okay, you just need to make the appropriate modifications. Later we will see why this method actually works. All right, it need not work always, but it works in many cases. It works. Okay, later we'll see why this actually works. It's because of a correspondence between quantum mechanics and classical mechanics, but more about that later. So for now, let's take the Hamiltonian as H equal to minus E divided by ME S vector dot B vector. Remember that the S vector here is the spin operator. Okay. So this is not a classical mechanical expression. We are using a quantum mechanical operator in here. We can make a further simplification. Let's take B vector to be a static uniform magnetic field and also in the Z direction. So let's write B vector is equal to B Z hat. Okay. So where Z hat is the unit vector along the Z direction. All right. Now let's substitute it back in here. Then H has the form minus EB divided by ME SZ. All right. Because S vector dot B vector, we write it as S vector dot B Z hat. So this is written as B multiplied by SZ. All right. B is just the magnitude that we take here, and this becomes BSZ. You substitute S vector dot B vector equal to BSZ in here, and we get the Hamiltonian as minus EB divided by ME multiplied by SZ. Okay. Now, just remember that E is taken to be less than 0 for electron. That's the convention that we shall use. All right. So, E has to be negative for the electron. Now here we see something interesting. The Hamiltonian operator and the SZ operator, they differ only by a multiplicative constant. All right, so they are proportional to each other. This means that they obviously commute. So it's clear that H commutes with SZ. H commutator of H with SZ is equal to 0. Okay. It's clearly because the difference between them, all right, is only a multiplicative constant. So again, as we said so many times, this means that the Hamiltonian and the SZ operators have common eigenstates. All right, the eigenkets of SZ are also eigenkets of the Hamiltonian. Okay. Now we have H is equal to minus EB divided by ME SZ. Okay. Now let's find the eigenkets of the Hamiltonian. Okay. We know that Hamiltonian and SZ have common eigenkets. We already know the eigenkets of SZ. Right? We know that SZ acting on ket plus gives you plus h bar by 2 multiplied by ket plus, and SZ acting on ket minus gives you minus h bar by 2 multiplied by ket minus. We know that SZ has only two possible measurement outcomes, plus h bar by 2 or minus h bar by 2. All right, these are exactly the eigenvalues that we have here. Okay. Now we know that ket plus and ket minus also have to be the eigenkets of the Hamiltonian, because the Hamiltonian and SZ commute. Let's find the eigenvalue. So let's take the action of the Hamiltonian on ket plus. This is equal to minus EB divided by ME SZ acting on ket plus. Okay, just substitute this for the Hamiltonian. Okay, and SZ acting on ket plus we already know. So this is minus EB divided by ME h bar by 2 ket plus. Okay, or we can write this as minus E h bar B divided by 2 ME ket plus. So H acting on ket plus gives you minus E h bar B divided by 2 ME multiplied by ket plus. Alright, so we see that the Hamiltonian acting on ket plus does not change the state, it just multiplies the state by a constant. Alright, and this constant is what we call the energy eigenvalue. Alright, so this energy eigenvalue we shall denote as E plus. Okay, so we have E plus is equal to minus E h bar B divided by 2 ME. Okay, this is the energy eigenvalue. Alright, there's one more possible energy eigenvalue, because you do the same thing for H acting on ket minus and you'll get, let's do this, H acting on ket minus, this is equal to minus EB divided by ME SZ acting on ket minus, and this action we already know, it's minus h bar by 2 multiplied by ket minus. Okay, so that minus will cancel with this minus and you'll get plus E h bar B divided by 2 ME multiplied by ket minus. All right, so we see that this is the second energy eigenvalue. All right, so we'll denote this like this: E plus minus. E plus is minus E h bar B divided by 2 ME, and E minus is plus E h bar B divided by 2 ME. All right, so compactly we'll write the two eigenvalues as E plus minus is equal to minus plus minus or plus E h bar B divided by 2 ME. We have the energy eigenvalues. Okay, so we have E plus is equal to minus E h bar B divided by 2 ME, and E minus is equal to E h bar B divided by 2 ME. All right, let's find the difference between these energy eigenvalues. All right, so if you look at E plus minus E minus, you get this is equal to minus E h bar B divided by 2 ME minus E h bar B divided by 2 ME, which is equal to minus 2 E h bar B divided by 2 ME, or simply this is equal to minus E h bar B divided by ME. Okay, so this is the difference in the energy eigenvalues. Now, since for the electron, right, E is negative, minus E here is positive. This is positive. Okay, so this minus E can also be written as, let me write it here, E plus minus E minus is equal to, this is modulus of E h bar B divided by ME, because minus of E, right, or minus 1 multiplied by E is positive for the electron, right? So we can write it also like this. Now, why did we find this energy difference, or the difference in energy eigenvalues? This is for a convenient definition, all right? You see that there's an h bar here, all right? So this has the units of energy. If we take E plus minus E minus divided by h bar, this has the units of angular frequency. We'll write it as omega, all right? And we'll define this omega as modulus E B divided by ME. Okay, that's what we have here. This is just a definition for later convenience. All right, so it's convenient to define omega in such a way that the difference in the two energy eigenvalues is h bar omega. All right. Now the difference in two energy eigenvalues is h bar omega. Okay. We had h is equal to minus EB divided by ME SZ. Since E is negative for the electron, we can write this as modulus E B divided by ME multiplied by SZ, and this is what we defined as omega. Alright, so the Hamiltonian can be put in a simpler form. We'll write this as H is equal to omega SZ, where omega is modulus EB divided by ME as we defined in the previous slide. Okay, not omega E, simply omega. Okay, this is omega. Now we have the Hamiltonian, we can find the time development operator. Okay, we know that we are talking about a case where the magnetic field does not depend on time, so the Hamiltonian is independent of time. Okay, so the time development operator has the simple form u of t comma 0 is equal to exponential minus IHT divided by h bar. We just substitute h equal to omega sz in here. We get u of t comma 0 is equal to exponential minus I omega sz divided by h bar. Okay, so we have now the time evolution operator. Now all information on time development is actually contained in this time evolution operator. Now we have the time evolution operator u of t comma 0 is equal to exponential minus I omega sz divided by h bar multiplied by t. So once we have the initial state, to find the state at any time, we just have to apply this time evolution operator to the initial state. We said that this is easy if we use the basis vectors in such a way that the base kets are also energy eigenkets. Okay, so we already know that the two operators that we have here are sz and h. They already commute. So we have a complete set of commuting observables which also commutes with the Hamiltonian. This means that the base kets that we must use in expanding the initial ket are the sz eigenkets, ket plus and ket minus, okay, which are also energy eigenkets. So let's say that the initial state is some linear combination of these basis vectors, ket plus and ket minus. All right, this is called the basis. So we can expand any vector in terms of this basis. Let's say that the initial state is given by ket alpha is equal to some linear combination of ket plus and ket minus. Okay, what about the state at a later time? So we have got ket alpha is equal to c plus ket plus plus c minus ket minus. These c plus and c minus are expansion coefficients. So this is a general initial state. Okay, what about the state at a later time? Ket alpha comma t0 equal to 0 at a later time t. This can be obtained by the effect of the time evolution operator on the initial ket. Okay, so let's write this as u of t comma 0 has the form exponential minus I omega sz divided by h bar. Okay, and here we have c plus ket plus plus c minus ket minus. Okay, now you just find the action of, so right, we know we have already done this. We have an operator in the exponential here and we have the eigenket of the operator here. All right, so we can use the eigenvalue equation. We have already used this. So c plus is a number, so this operator passes this number, it commutes with this number. So we can write the first term as c plus exponential minus I omega sz divided by h bar acting on ket plus and then plus c minus exponential minus I omega sz divided by h bar acting on ket minus. Okay, now we use this is equal to c plus exponential minus I omega divided by h bar, this sz acting on ket plus. All right, we can use the eigenvalue equation here, so you will get the exponential of the eigenvalue. All right, this is the exponential of the operator acting on the eigenket of the operator. We already showed that this gives us the exponential of the eigenvalue multiplied by the eigenket. Okay, so you substitute by the eigenvalue plus h bar by 2 t acting multiplied by ket plus plus c minus plus, let me write it here, plus c minus exponential minus I omega divided by h bar. So the eigenvalue here is minus h bar by 2. You also have the t here multiplied by ket minus. We see that this h bar and the h bar cancel here, here also. All right. There's a minus here and a minus here. All right. So this now has the form. Let me write it here. Ket alpha comma t0 equal to 0 at time t is equal to c plus exponential minus I omega t divided by 2 multiplied by ket plus c minus exponential I omega t divided by 2 multiplied by ket minus. So this is the generic state at any later time given the general state like this, given the general initial state like this. Okay. So this is how time evolution operator acts on ket alpha. So and we get the state at any later time. We see that, as we said again, the expansion coefficients here, they have just been modified by this phase factor. Okay, the expansion coefficients at that we had at time t equal to 0 are modified by getting multiplied by a pure phase factor. They are phase modulated. That's the only thing that has happened. The expansion coefficients have changed. All right, here. All right. Now this is what we have done. We started with the generic state ket alpha equal to c plus ket plus c minus ket minus. This is the initial state expanded in terms of the chosen basis. Okay, and we said that the time evolution operator has the form u of t comma 0 is equal to exponential minus I omega sz divided by h bar multiplied by t. And we found the state at any later time alpha comma t0 equal to 0 at a later time t is equal to u of t comma 0 acting on ket alpha. Okay, we used the eigenvalue equation and we found the state at any later time as this expansion of the base case. All right, we are expanding the state at the later time using the same basis ket plus and ket minus, and we see that the only thing that has happened is that the expansion coefficients have been modified. All right, and we have used the eigenvalue equation for the Hamiltonian. All right, given the initial ket alpha is equal to c plus ket plus c minus ket minus, the state at a later time is given by this expression. Okay, now suppose that the initial ket represents the spin up state. All right, spin up state is the name we use for the sz plus state or the eigenket of sz operator with eigenvalue plus h bar by 2. This is called the spin up state and it's denoted by ket plus. Right? Now suppose the initial state is ket plus. This means that c minus is 0 and c plus is 1. Okay, so we are talking about the initial state ket alpha is equal to ket plus. Then the state at a later time, if you take c minus equal to 0, the state at a later time is simply exponential minus I omega t divided by 2 multiplied by ket plus. Okay, so this is exactly the same state. It gets multiplied by a pure phase factor, but it represents exactly the same state. So the state does not change. All right, the modulus of the expansion coefficient is also 1. Okay, so the normalization also does not change. So if we start with a spin-up state, the system will remain in a spin-up state. Okay, this is not surprising because this is a stationary state. It's an energy eigenket. This is what happens to an energy eigenket. Okay. Next, let's suppose that initially the system is in the Sx plus state. That means that the system is in the state represented by ket Sx plus, an eigenket of the Sx operator. We have seen in the first chapter that the eigenket of Sx operator is a linear combination of the eigenkets of the Sz operator. We know how exactly it has to be expanded. We saw earlier that ket Sx plus can be written as 1 by root 2 ket plus 1 by root 2 ket minus. This is something that we have seen in the first chapter. Now compare this with the state ket alpha is equal to c plus ket plus c minus ket minus. This means that we are talking, right? We are talking about the case where c plus is 1 by root 2 and c minus is also 1 divided by root 2. So the state that we are considering now as the initial state corresponds to c plus equal to c minus equal to 1 divided by root 2. Now Now what happens to this state at a later time? You just have to put c plus equal to 1 by root 2 and c minus equal to 1 by root 2 in this expression. Okay, so that means that the state at a later time in this case is given by get alpha comma t0 equal to 0 at time t is equal to 1 by root 2 exponential minus I omega t by 2 get plus 1 by root 2 exponential I omega t divided by 2 get minus. Okay. So if we start with the state get Sx plus, we saw that it will evolve at a later time to a state given by get alpha comma t0 at time t. Okay, the expression for that state is given here. Initially, if you made a measurement of observable Sx or the x component of spin on this state, you would be sure to get plus h bar by 2 because this is an eigenket of the operator Sx. So an initial measurement of the x component of spin would give you plus h bar by 2 with probability 1 and minus h bar by 2 with probability 0. Alright. Now what happens if you make a measurement of Sx on the time evolved state? Or what happens if you make a measurement of the x component of spin on this state? Okay. We know that by the measurement postulate, if you measure Sx on this state, alpha comma t0 time t, if you make a measurement of Sx on this state, it will reduce to get Sx plus with probability. This is the probability postulate that we saw in the first chapter, right? It will change, the state will change to get Sx plus with probability given by, this is the probability postulate, modulus square of bra Sx plus get alpha comma t0 time t. Okay, and it will change to get Sx minus with probability given by this, all right, bar Sx minus get alpha comma t0 t modulus squared. All right. Now whatever appears inside is usually referred to as the probability amplitude because you get the probability by taking the modulus square of this. So this is called the probability amplitude. Probability amplitude. Okay. So we can first find the probability amplitude for each of the possibilities. The probability amplitude for measuring plus h bar by 2 is the same as the probability amplitude that the system changes to get Sx plus. Okay, because if the system changes to get Sx plus, then we would surely get plus h bar by 2. If the system changes to get Sx minus, we would get minus h bar by 2. So the probability amplitude for finding plus h bar by 2 is the same as the probability amplitude that the state changes to get Sx plus. And this probability amplitude is given by the component of the given state along get Sx plus. All right. So what we get here is the component of get alpha comma t0 at time t along get Sx plus. Now how do you find this component? You take the inner product bar Sx plus get alpha comma t0 at time t. All right. So this is the probability amplitude for getting a value plus h bar by 2 or equivalently for the system to change to a state get Sx plus. All right. So you just calculate this inner product. We can write bar Sx plus like this. You just use the early expression for get Sx plus and find the corresponding bra. It is 1 by root 2 bra plus 1 by root 2 bra minus. Okay. And get alpha comma t0 at time t is given by this expression here. Okay. Now you take the inner product. We can use the orthonormality, which means that bra plus get plus is equal to 1, bra plus ket minus is equal to 0, bra minus ket minus is equal to 1. Okay, so you see that bra plus will give you 1. This combination will give 1. Bra plus ket minus will give you 0. Similarly, this term also, right? Bra minus ket plus also will give you 0, which means that the cross terms are all 0. Okay, so if you take this inner product, you are just left with, here you have a 1 by root 2, 1 by root 2, which gets multiplied to 1 by 2. And here you have an exponential minus I omega t divided by 2, which is a number, which also appears here. So that's exponential minus I omega t divided by 2. The only multiplication we have is bra plus ket plus. which is equal to 1 because these are orthonormal state. Okay, so this multiplication gives us 1 by 2 exponential minus I omega t divided by 2, and these two terms multiply to give 1 by 2 exponential I omega t divided by 2. Okay, the cos terms are all 0 because of orthogonality. Okay, now we can add these two terms. All right, you just use this expression. This is equal to, okay, this is equal to half. You just expand this exponential in terms of sine and cosine. So this expansion you already know. This is half cos omega t divided by 2 plus I sine omega t divided by 2. Okay, here also there's a half which I have taken outside. This, so it's exponential minus, so it's a minus here. Now this is expanded. The second term is expanded to again cos omega t divided by 2 plus I sine omega t divided by 2. These two terms cancel, the sine terms cancel, and you are left with twice cos omega t divided by 2. There's a 1 by 2 here. So the 2 gets cancelled and the final result is cos omega t divided by 2. Okay. So we see that the probability amplitude for measuring plus h bar by 2 is cos omega t divided by 2 for this state. Okay. Initially, the probability amplitude for measuring plus h bar by 2 was 1. If you measured Sx on the initial state, the probability for plus h bar by 2 was 1. Okay. But at a later time, the state has evolved. Now, the probability for measuring plus h bar by 2 is cos omega t divided by 2. Okay. And we say that at t equal to 0, if you just put t equal to 0, we get 1, which was the probability for measuring plus h bar by 2 at time t equal to t0. Sorry, t equal to 0. Okay. Now I hope this is clear. In the same way, you can calculate the probability amplitude for finding minus h bar by 2 if you measure the x component of spin or Sx on the state get alpha comma t0 at time t. Okay. Now this probability amplitude is given by bra Sx minus get alpha comma t0 time t. So this is just the component of the state along get Sx minus, or the projection of the state get alpha comma t0 at time t onto get Sx minus. Okay. Now for this you can use the expression get Sx minus equal to 1 by root 2 get plus minus 1 by root 2 get minus. You can find the corresponding bra, use the expression for the state at a later time t, okay, and then calculate this probability amplitude. All right. Now clearly this, the only difference from the previous calculation is that you'll get a minus sign here instead of a plus sign in the previous expression. All right. You can check this. I leave it as an exercise for you to calculate this component or this inner product. Okay. Now if you use the same expansion, you get this probability amplitude as minus I sine omega t divided by 2. Okay. Again, at t equal to 0, you see that the probability amplitude was also 0. Okay. Now we have the probability amplitudes bar Sx plus get alpha comma t0 time t is equal to cos omega t divided by 2. Okay. And bar Sx minus get alpha comma t0 at time t is equal to sine omega t divided by 2. Okay. Now you notice one thing, that initially, all right, the initial state was get Sx plus. Now initially the probability amplitude for measuring minus h bar by 2 was 0. All right, because the initial state is get Sx plus. The probability that the system changes to get Sx minus, okay, this is 0 by orthogonality. Now after some time, you see that the state picks up a component along get Sx minus also. All right. Initially, there was no component along Sx minus, but after some time, the state of the system picks up a component along get Sx minus also, and that component is given by, oh, I think I missed a minus I here, minus I sine omega t divided by 2. Okay. We can find the corresponding probabilities by taking the modulus squares of this probability amplitudes. Okay, so you take the modulus square of this probability amplitude, you get cos square omega t divided by 2 for measuring plus h bar by 2, and sine square omega t divided by 2 for measuring Sx minus. Okay, or sorry, for measuring minus h bar by 2 along the x direction. In other words, you get the probability cos square omega t divided by 2 for the system to be found in the state get Sx plus, and sin square omega t divided by 2 for the system to be found in the state get Sx minus. Okay. So these are the probabilities for the system to be found in the Sx plus minus state at some later time t. Right, this is just the probability postulate of quantum mechanics that we have seen in our first chapter. All right, if you don't remember it, please go and revise those parts. We conclude that even though the spin is initially in the positive x direction, the magnetic field in the z direction causes it to rotate. As a result, we obtain a finite probability for finding Sx minus at some later time. So even though we started with the state get Sx plus, after some time there's a probability. If you make a measurement of the x component of spin, there's a probability for finding the system in the state get Sx minus. That's after some time, not initially. Initially the probability is 0, but after some time there is a non-zero probability for finding the system in the state get Sx minus if you make a measurement of the x component of spin. Okay, so the explanation is that the magnetic field in the z direction has rotated the spin in such a way that the system or the state picks up a non-zero component along get Sx minus also. Okay, now these probabilities are cos square omega t by 2 and sin square omega by 2, omega t divided by 2. You see that if you add these up, the sum of the probabilities still adds up to 1. So initially the probabilities were 1 and 0. Now the probabilities at a later time t, the probabilities are cos square omega t by 2 and sin square omega t by 2. Initially also the probabilities added up to 1. At a later time also the probabilities add up to 1. Okay. Now this is in agreement with the unitarity property of the time evolution operator. Now this is exactly what we demanded in the beginning, that the sum of the probabilities always add up to 1. Right? The sum of the probabilities in the given corresponding to the given state always add up to 1. Okay. We can now calculate the expectation value for the x component of spin. Okay. The possible measurement outcomes are plus h bar by 2 and minus h bar by 2. And we know that the probabilities for obtaining plus h bar by 2 is equal to cos square omega t by 2, and the probability for obtaining minus h bar by 2 is equal to sin square omega t divided by 2. Now what's the expectation value? Expectation value or the average value. All right, this is just the weighted sum of the possible measurement outcomes. And what's the weight given? The weight given is the probabilities. So you multiply, you take each measurement outcome, multiply it with the probability and add them. That's what gives you the expectation value. All right, again, this is something that we have discussed in detail in the first chapter. Okay, so the expectation value of Sx denoted using this symbol is equal to probability of measuring plus h bar by 2 multiplied by h bar by 2 plus probability of measuring minus h bar by 2 multiplied by minus h bar by 2. Okay, this is equal to, this probability is cos square omega t divided by 2 multiplied by h bar by 2 plus sin square omega t by 2 multiplied by minus h bar by 2. Right, you can take the h bar by 2 outside, and then you have cos square omega t divided by 2 minus sin square omega t divided by 2. Now we can use the trigonometric identity. We know that cos square x minus sin square x is an expression for cos 2x. Okay, so this gives h bar by 2 cos 2 omega t divided by 2 or cos omega t. Okay, so the expectation value for Sx is given as h bar by 2 cos omega t. Okay, that's the expectation value for Sx. We see that the expectation value of Sx changes with time. Initially at t equal to 0 it was h bar by 2. Now the expectation value is changing with time. All right, it is time dependent. Now we can also find the expectation value using the basic formula, the basic definition for expectation value. We know that expectation value of Sx in the state alpha is given by, in the state get alpha comma t0 equal to 0 at time t. Okay, it's given by bra alpha comma t0 equal to, or simply let's write it briefly, bra alpha comma t0 time t operator sx and get alpha comma t0 at time t. This is actually the definition for expectation value. You can of course get the same result by carrying out this calculation also. All you need is the form of operator sx. Okay, now we can write Sx conveniently in this form. This is again something that we saw in the first chapter. We saw that operator Sx can be written in terms of get plus bra plus etc. in this manner. Okay, so you just use the expression for get alpha comma t0 at time t and the expression for Sx in this form. All right, and you can calculate the expectation value of Sx using this formula also. All right, so I want you to check that this calculation also gives back exactly the same result. Right? I leave it again as an exercise for you to practice. Okay. So we have expectation value of Sx equal to h bar by 2 cos omega t. Right? Cos omega t is oscillatory and we know that cos omega t varies like this. At t equal to 0, cos omega t is 1 and at omega t equal to pi by 2 it drops to 0 and then goes to minus 1 and oscillates like that. Okay, so we see that at omega t equal to 0, the expectation value for Sx is simply h bar by 2. The reason for this is that at t equal to 0, the state we said was get Sx plus, and at this time, the probability for plus h bar by 2 is 1, and the probability for minus h bar by 2 is 0. Now, as the time goes, and let's say when omega t becomes pi by 2, then the expectation value of Sx drops to 0, right? Because omega pi cos pi by 2 is 0. So at this point, when omega t equal to pi by 2, the expectation value drops to 0. This is because the expectation value, the probability for plus h bar by 2 becomes equal to the probability for minus h bar by 2. Okay, it becomes equal to probability for minus h bar by 2 when omega t is equal to pi by 2. Okay, so we see that these probabilities are changing. Right, now this is an oscillatory function. This means that the expectation value of Sx oscillates in time. The angular frequency of oscillation is denoted by omega, and we saw that omega is equal to E plus minus E minus divided by h bar. Okay, it's the difference of the two energy eigenvalues divided by h bar. Now this is in agreement with what we saw when we discussed the time evolution of expectation values. Right, we saw that the expectation values oscillate in time and the oscillation frequencies are determined by the difference in energy eigenvalues. Right, so you can compare this with the general treatment that we had when we discussed the time evolution of expectation values. Now in the same manner, you can also find the expectation value for Sy, and it turns out to be h bar divided by 2 sine omega t. We see that the expectation value of Sy also changes. Initially it is 0, okay, and then it goes to, let's say at omega t equal to pi by 2, it goes to plus h bar by 2, and then it goes to minus h bar by 2, etc. It oscillates in time with the same angular frequency, okay. Now, how do you calculate this? You can calculate it just as we did in the when we calculated the expectation value for Sx. All right, you can write this as probability. Again, when you measure Sy, you expect either plus h bar by 2 or minus h bar by 2. All right, and the probabilities can be written as, so the expectation value of Sy can be calculated like this. This is bra Sy plus get alpha comma t0 time t. This is the probability for measuring plus h bar by 2. Okay, so multiplied by h bar by 2. So this is p of h bar by 2 multiplied by h bar by 2 plus p of minus h bar by 2. So it would be a modulus square of sy minus alpha comma t0 time t modulus squared, okay, multiplied by minus h bar by 2. Okay, this would give the expectation value for Sy. Okay, this is simply again P of h bar by 2 multiplied by h bar by 2 plus P of minus h bar by 2 multiplied by minus h bar by 2. Okay, and you can use this expression for get Sy plus or minus is given by 1 by root 2 get plus or minus I by root 2 get minus. Okay, this is something again that we saw in the first chapter. You can use this expression, calculate this to obtain, to find the expectation value of Sy. All right, again, I leave the details of the calculation as an exercise. You can check and show that expectation value of Sy is indeed h bar by 2 sine omega t. So we see that both Sx and Sy, the expectation values of Sx and Sy, change in time. All right. Now you can alternately calculate expectation value of Sy like this also. All right. Again, I ask you to do it by yourself to get some practice. The expectation value of Sy can also be calculated like this. Bra alpha comma t0 time t operator Sy get alpha comma t0 time t. Now for the expression for Sy, the operator Sy, you can use this expression, which again we obtained in the first chapter. Okay, so you can calculate it in any way and show that they all give the same result, h bar by 2 sine omega t. Okay, now if you calculate the expectation value for Sz, you see that it's equal to 0. Okay, this can be calculated like this. For example, all right, we have got bra alpha comma t0 time t and then operator Sz and then ket alpha comma t0 at time t. All right. Now, since this ket alpha comma t0 at time t is expanded in terms of the eigenkets of Hz, you can use the eigenvalue equation and then find this value. All right. You'll see that it's equal to 0. This means that at all times, the probability for plus h bar by 2 along the z direction is equal to the probability for minus h bar by 2. Okay, again, this is left as an exercise. Please calculate this. If you have any problem with the calculation, let me know. All right, so this essentially means that at all times the probability for plus h bar by 2 is equal to the probability for minus h bar by 2. Okay, this is the reason why the expectation value of Sz is 0 always. It's 0 at all times. Okay, so the expectation value for Sz does not change, but the expectation value for Sx and Sy change with time. This means that the spin actually rotates or precesses in the xy plane. All right, that's how we explain how the expectation values change with time. All right, the expectation value of Sz does not change. This is the reason why we say that it rotates in the xy plane. Okay, so initially the spin could be the state of the system could be along ket Sx plus, and slowly it evolves into superposition of ket Sx plus and ket Sx minus, and then after some time it will become ket Sx minus. Right, so it rotates. Similarly, the expectation value for Sy also changes. Okay, so physically this means that the spin actually precesses in the xy plane. For example, it could be initially in this direction and then rotated to another direction and then keeps rotating. Right? This is the reason why expectation value of Sx and expectation value of Sy changes with time in this manner. Okay. We discussed the example of an electron in an external magnetic field. Right? We started with the Hamiltonian. We showed first that the Hamiltonian can be written in this form: H is equal to omega Sz, where omega was modulus E B divided by ME. Okay, so the time evolution operator has the form u of t comma 0 is equal to exponential minus I omega Sz divided by h bar. Okay. Now, since h is a multiple of Sz, this means that h commutes with Sz. All right. So they have common eigenkets. So the eigenkets of Sz are also eigenkets of the Hamiltonian. Okay. So we said that it is convenient to use the basis ket plus comma ket minus. These are the bases. These are the base vectors. All right. Now we consider a general initial state ket alpha equal to c plus ket plus c minus ket minus. Okay, and we applied the time evolution operator to this and showed that at a later time alpha comma t0 t, this is equal to c plus exponential minus I omega t divided by 2 ket plus c minus exponential I omega t divided by 2 ket minus. Okay, this is the time evolved state. Now we consider different cases. We first took the case where c plus is 1 and c minus equal to 0. Okay, this means that ket alpha is simply ket plus, right? And we saw that the time evolution does not change the state. Okay, the state is a stationary state, we said. All right, so time evolution does not change the state. Then we considered the case where ket alpha is equal to ket sx plus. This corresponded to c plus equal to c minus equal to 1 divided by root 2. Now we found the state at a later time, ket alpha comma t0 time t. We saw that this is equal to 1 by root 2. Just put c plus equal to 1 by root 2 and c minus equal to 1 by root 2 in here. So it's 1 by root 2 exponential minus I omega t divided by 2 plus 1 by root 2 exponential I omega t divided by 2. So there's a ket plus here and a ket minus here. Okay. Then we went on to calculate the probabilities, right? Probabilities for measuring plus h bar by 2 and minus h bar by 2 if you measure Sx, right? So we on measuring the x component of spin, we calculated the probabilities for finding plus h bar by 2 and minus h bar by 2. From that, we calculated the expectation values, and we saw that the expectation value of the x component of spin actually changes with time. It oscillates in time. It's equal to h bar by 2 cos omega t. We also find that the expectation value of Sy is equal to h bar by 2 sine omega t. Okay. We also got expectation value of Sz equal to 0. This remains the same at all times. Okay. So the explanation is that the spin actually precesses in the xy plane. Right. So the spin precesses in the xy plane. This is the reason why even if we start with the state ket sx plus, after some time it picks up a component along ket sx minus, etc. All right. And the oscillation of the expectation values is in agreement with what we discussed when we talked about the time dependence of expectation values. Okay. So with that, I shall conclude this discussion. Thank you.